Good afternoon, everyone. So, welcome to the week 9 lecture, week 9 problem solving session. So, like the previous weeks, we'll be just going to revise some of the contents from this week content, and we'll be just solving the last year assignment problems so that it will be helping you to solve the assignment problems. So, this week was mostly was about natural language processing. Okay. So the first thing we are going to be seeing is the one hot representation. The second thing is distributed representation of words. The next stuff we are going to be looking was SVD for learning the word representation. And then we'll be looking the continuous bag of words model, basically. Then skip glum model we are going to be looking into. And contestive estimation. Then hierarchy softmax. Then lastly, the globe representation, which was commonly used in 2015 for processing the natural word language. Then lastly, we'll be looking into some of the problem statement from the last year. Okay. Okay. So let's start looking to the material basically. So first of all, why we need a representation of the words? So that's the basic question. Okay. So the thing is basically any sentence in the any language we have a means alphabets, and using the alphabets we have a language means we make a words, and using the words we construct a sentence which conveys some meanings. Okay. So we have alphabets using which we make a words and sentence. So the thing is, every word has a unique meaning, and after every word, there is only means not every word just suited that. Okay, so there is a means whole grammar and whole semantic meaning is associated with each word, sentence, what it want to convey the meaning basically. Okay, so the thing is, we can't directly use the words, alphabet, and sentence to directly make a model to them. Okay. So the basic thing is it all has some words, okay? But the thing is the model expect everything to be in the form of some numerical representation, gives some meanings. Okay, you can't directly pass the A to the model, okay? Because basically we are working with algorithms, mathematical algorithms. So everything should be in the form of certain representation should be there so that we can process using our black box model. Okay, so it should have a numerical representation basically. So the technique which was covered this week was mainly associated, which was tried very early on in the natural language processing. So in the chat GPT, for example, you give certain words and it predicts the next words basically. Okay, but it does not understand the word actually. It understands its numerical representation basically. The model knows that if my word is there, okay, any word, for example, dummy word, it is represented using some vector form. Okay, it is having a certain representation. So the ML model runs the vector, and what's the next word you need to predict? Okay, that is also a vector. So the whole task is that you have been given a bunch of vectors, okay, and how it given certain vector, what's the probability you want to what's the next vector can be there. Okay, it's not like after each and every word, the next word there should be grammar or semantic meaning should be there. Okay, so our model expect everything to be in the numerical representation form. Okay, so to run the representation, we be looking at how to convert the words into a numerical representation. Okay. Words to certain numbers form, basically numbers, vectors. Okay. So this is the main challenge actually. What's the best way of converting it? Okay. So the technique which was covered was mainly tried in the early stage of the research in the natural language processing community. Okay. So I hope it's clear that we have been given a words. We want to map each word to a certain representation, certain vectors or certain numerical representation. Okay, and that numerical representation we are passing to our model, and then we can do the several task that was predicting the next word. Okay, classifying the sentences. Okay, so that all will be coming into picture after that. So first we have a numerical representation of the data. So unlike image data, where we have been given a pixel value, RGB value, in the natural language processing, usually we have a flexibility to run this numerical representation for each word. Unlike image thing, because in image the pixel value it is already fixed. That's how we have represented the image as it is. But here we have a very much flexibility to run the numerical representation of each and word as well. So that provides a very much freedom to run any kind of a representation, so that we can underline and we can make a grammar semantic meaning out of it basically. So the first technique we'll be looking into will be one-hot representation of words. Okay. So the thing is, so for example, in each and every language we have they are defined word already. There's a vocabulary of the words which are already defined in the corpus, basically. So we have a bunch of words out there. Okay. So they cannot be any other word which have a semantic meaning as defined in the language. Okay. So we have been have a large corpus of words which we call as a vocabulary, basically. So which I will be denoting by the capital letter V. Okay. And our task is to convert each and every word in this vocabulary to a numeric vector form. Okay, so basically we want to run a function, okay, which takes a vocabulary as an input and tries to predict the numerical representation of the input, basically. So here I have written r to the power n in the Euclidean space, basically. Okay, so where n can be arbitrary, it can be very large and all. Basically, we want to run this function, which can help us convert the words to a vector. And once we have a vector, we can do a lot of different tasks and all this develop different algorithm basically. For this vocabulary, the bunch of collection of this different words and it's called basically the vocabulary and the sentence are there. We have been given a bunch of sentences. Okay, and which has already have been we have been writing from the means from from when we started developing this language. So we have already predefined a lot of sentences, its and its meaning, semantic means what's the grammatically it's correct or not. So we already know all of this. And the correction of such sentences and all, we have it's basically represented as a corpus, basically. Okay. So I hope that it's very much clear that we need to construct a function which take words as an input and try to predict as a vector form of it. Okay. And the size of the vocabulary I will be denoting is by a double line. So this will denote the size of the vocabulary, okay, which has already been defined. We can't, means for example, the alphabets, there are only 26 alphabets, basically. We can't have more than 26 alphabets, okay, in English. Okay. So the basic thing in the word representation is that we can represent any sentence, okay, any word basically with the vector of the form 0 and 1s. Okay. So for example, we'll be constructing a vector which will be in the dimension r to the power size of the vocabulary. Okay. We'll be assigning a vector to that much dimensions basically. And each vector will be of the form zeros and ones basically. Okay. So it will each vector will always have only means one of its index will be one and the rest of the index will be zeros. So basically, for example, if we have a cat, for example, okay, so we will be representing cat in the 0, 0, and at certain index it will be 1, and after all it will be zeros. Okay, so let's take a common example to understand it more properly. What's happening actually? Okay, suppose I have only three words. Okay, means two words are there, cat and dog basically. In the vocabulary, I have a two words, okay, and these two words I want to convert into a vector representation, okay. So the task is basically I need to take one of the element of this vocabulary and try to construct a vector out of it, okay. So the thing is, in the one-out representation, we will be representing cat as the size of the vocabulary in this example is two only. We have only two words. So I will be representing as a vector as 0, comma 1 for the cat. And dog, suppose I will be representing as 1, comma 0. So I have a unique representation for each and every words. Okay. So that's how this is one of the mapping. And there is nothing illegal about this mapping actually. It's all until unless you make sure that each and every word has a unique representation. Every representation is means it's fine. You can have a 0, comma 1, okay. And also you can have means it should be different basically. Okay. That both of the representation should be different for different words. And it should be a one-to-one mapping between the words and the vectors. It should not be that two words are mapping to the same vectors. Okay. So that should not be happening. So any kind of such functions you are having, then that satisfy as kind of a convergence that satisfy the criteria of basically that what we want to have. But there is a lot of drawbacks of having this kind of an representation. The thing is, the firstly, this representation it's arbitrary. Okay, it does not means we have randomly assigned 0, comma 1 to a cat and 1, comma 0 to the dog. Okay, so we can do 1, comma 0 to the cat as well or 0, comma 1. So there is means mismatch can be happening. Okay, there is nothing like that. You can't change the representation. So it is not unique actually, this representation. we can just rearrange the representation and again we can pass it to our model. Okay. But the thing is also it does not capture the similarity we are having, means semantic meanings we are having actually. So for example, the cat, dogs, they all are animals. Okay. So we want to have more meanings to our representation basically. So that's the basic task. So for example, the cat and dog is there. Their representation should be very much in the notion of distance, it should be closer by. Okay. Because if we have a cat and dog in the vector representation in 2D, if we see, okay, it should be very much nearby. And if we have a car or a truck, so it should be far apart from the cat and dog. Because we know that car and truck, they are vehicle, okay, and cat and dog, they are animals. So like that, we should have, means if we can able to represent such meaningful semantic meanings to the vector. Okay, so that's the basic task. Otherwise, this conversion will also work fine. Okay, but it does not capture the semantic meanings which we want our representation to have. And the main drawback for this method, one-hot representation, is that, as we mentioned, that we are means assigning one-to-one mapping between a binary string to a word. Okay, but and also the Euclidean distance, the L2 norm between any two words. If we see, it's always U2. It's always constant. Okay, so which always says that cat and dog are same as nearby in the representation as dog and truck. Every words are, means very much nearby actually. Okay, so it does not means represent any kind of an information basically of different word that two similar words should have a near, means their Euclidean distance should be nearby. Okay. And one more thing is if our vocabulary size increases a lot, the number of words we are having, okay, then there is an exponential increase in the dimension for the representation. If we have a 50K, then we'll be representing our means a word in our vocabulary using r to the power 50 dimension, string of 50 from 50K dimensions. And working with that higher dimension doesn't make sense computationally. It's very much expensive. Okay. So the question we are asking here is that can we do better? Okay. Can we have a more meaningful word? Okay, on a lesser dimension which capture the semantic meaningful, and we can measure the distance and how much two words are similar. Okay. So to know that how much two vectors are similar, there is one thing we are going to be defining is cosine similarity between the two vectors. Okay. So cosine similarity is a function basically, okay, which takes a two vector u and v, and it's all it just give a means normalized uh, dot product basically at u transpose v and norm of u norm of v. Okay, so this is how the cosine similarity is defined between two vectors. So we are measuring that how much two vectors, if we project one vector on the top of other vector, how much they are correlated. There is a correlation we are trying to measure. Okay. In this one-hot representation, the two vectors are always orthogonal. Okay. The cosine similarity is always zero. So that's why we do not have a semantic meaning between dog and cat. It's always zero. But we want to have a certain relation between that how much cat and dog they are nearby in the representation. Okay. So that was the very first model which was developed. Okay, and that's kind of a very much brute force. Okay, that's how the research have progressed over the years. Okay, so the next thing we are going to be seeing is the distributed representation of words. Okay, so the thing is, for example, if we take a certain sentence, okay, so for example, a bank is a financial institute that accept deposit from the public and create credit. Okay, so here we are having a different bunch of words, basically, okay? And whenever bank is there, the financial, deposit, credit, okay? this all words are kind of a correlated. Okay, correlated in the sense that whenever a bank is there in a sentence, the financial deposit and credit, this all words automatically is very much, it make a subset which automatically correlates with it. Okay. So the question is, can we model something that using the different word information also, we can model the representation of our words? Okay. So that's the question we are trying to ask. So the question is, for example, the man is there. The man is having a two legs. Okay. Two legs are there, man, woman. Okay. So whenever means now a human being we talk about men, women, legs, hands, this all have a semantic meanings. This cluster of words. Okay. So we want to associate a representation so that the bunch of similar words which have a semantic kind of a similar meaning, the representation should be very much close by. Okay. So in the distributed representation for this thing, for converting a word to a vector form, we are going to be defining something as a co-occurrence matrix. Okay. So as I mentioned, for example, the sentence, the financial deposit, credit, okay, this all represent means they have been very much correlated with the bank. Okay. So the co-occurrence matrix is that we want to, for example, each and every word, we want to measure the similarity and construct a matrix out of it. Okay. So how we are going to be doing that? Okay. So as I mentioned, we have been given a corpus, which have been a bunch of sentences we have been given. Okay. And the for example, and a co-occurrence matrix is just term cross term matrix. So I'm trying to use the same notation as it was used in the lecture so that it will be easier for you to follow what I'm meaning. Okay. Okay, which capture the number of times a term appear in the context of other term. Okay. So it makes a intuitive sense as well. Okay. For example, as I mentioned, the bank deposit. So we want to measure that whenever the bank is there, how many times the credit word is coming the corpus. So corpus we are having, which are just a bunch of sentences. Okay, which gives us that this are the sentences which have been semantically defined already. Okay. So we want to construct a co-occurrence matrix which is of the form of term by term, which is the size of vocabulary, source of vocabulary. Okay, which we measure that how much time each and every means two terms are correlated, kind of a similarity we want to measure. Okay, so first of all, we will defining a context. Okay, because otherwise there are different words, different sentences might have a different number of words. Some is having a 10, 20, 100, something like that. Okay. So first of all, we are gonna be constructing us. For example, we have been given a bunch of sentences. So one sentence, let me take user opinion of computer system response time. Okay. So this is one of the sentence. Okay. So first of all, we are been defining a context length. So for example, I'll be defining a context length of 4. This is my first context length. This is my second context length. Okay. This is my third context length. Okay. Context size basically. Okay. So we have been defining that how many times a word and that context have been occurred. Okay. So for example, the turn cost term is there. Context end, we can take it to be infinite as well. But we don't want that basically. Okay. We want to just take a last 10. It should be sensible enough. It should be computationally efficient. Okay. So for example, human. machine, system. Okay. So we have defined the words. What are the word basically? We have defined the context size. It's a collection of words basically, okay, of certain length. Now we will gonna be means splitting a corpus into make a bunch of uh, context basically context length of some four sentences. So suppose I take a context size of 4. Then we are going to be dividing our corpus into a larger size of corpus. Each one of them is having a 4 words, which are consecutively is occurring. Okay. So we are having a word, we are having a context associated with each word. Okay. And we will be defining something as, for example, whenever the computer is there. Okay. So in that particular context length of 4, how many times the user word have been defined. So that is kind of I'm counting. Okay. So I will be having a corpus. Corpus will be having a sentence. We'll be having of certain context in of suppose 4. Okay. And we'll be having a bunch of examples. Then we are going to be asking that how much time in that particular context that, for example, human is there. Okay. In this case, how many time in the context in the 4 human and human they have occurred altogether, both of them. Okay. And there is a rare chance that in just a context and the 4th human and human will be coming. So it's a 0 basically. Human and machine suppose 1. So some random kind of a matrix we'll be getting. Okay. So this whole matrix we are just calling as a co-occurrence matrix. That given a particular context length, how much time each in that particular context length that 2 words have been occurring all together. Okay. So you can choose the set of words and context to be the same or different. It depends. Okay. That whether you want to have a words cross words, basically, you want to measure the similarity between any 2 words in the vocabulary we are having, or the context, basically, it's give us the information that if this word is there, with this word, automatically the next word always occurred. Okay. So the each row of the co-occurrence matrix give a vectorial representation of the corresponding word. Okay. So each row is giving us some representation also. Okay. And that is what we wanted. And no of these 2 vectors will be having the same, means it's a one-to-one correspondence, basically. That's what we wanted, bijective. Okay. So, and but there are certain problems with this approach. Okay. The thing is, for example, in normal sentences, we have a, the, for. These are very frequent words in the normal sentences, which is every time getting used. So the frequency of this word will be, the count of for this word will be very much high in this co-occurrence matrix. Okay. So one possible solution is just to ignore very frequent words. We can just remove from the in that particular context and a and the for that words, which are very much frequently used. Okay. Or the second solution is that we can use the threshold. We can define that the maximum count we can have for the particular word and the context is suppose 10, not more than it. Okay. So that's the second solution we can have. Or instead that we can define means for the particular word and the particular context instead of count, because that was that what is what we were using. Okay. We were defining PMI between the word and the context. Okay. So what is an PMI basically? Okay. So PMI between a word and the context is defined as a log of probability of context given word divided by probability of context. So it's kind of a conditional probability we are defining it. Okay. So we had what we are saying is that if we simplify it further, this probability of context given word, okay, it will be log of count of word comma context times the n, where is the n is the total number of words, divided by count of context times count of word. So it's kind of a, we are measuring the relative frequency of word and context given total number of counts of for the context and the word. So we have been given a corpus. We just divide our context length of size certain, for example, 4. And we will be counting that for this particular word and this context, how many they both were frequently means occurring together. So that will be giving us the count of word and context. We can also count that in all the sentences, what's the total count of particular context and what's the count of count for particular word. And this n is just a normalizing constant kind of stuff. Okay. So it does the work basically what we want. Okay. And it's also one of the solution. Okay. We can't say that it's better than the previous two what we discussed, that we can have a maximum threshold and all, or we can remove the frequent used word. But it all depends that which one works for a particular kind of a size of bags of words, basically. So there's a drawback for this PMI. The fundamental drawback is that we have defined in the form of ratios. Okay. If my count for the word and context is 0, okay, there is a fair possibility because our matrix will be very sparse. Okay. So the PMI will be minus infinity because log 0 is minus infinity. Okay. So the thing is, means instead of that, 2 does not fall into that loop. We will be defining PMI is 0 whenever the count for the particular word and context is 0 instead of minus infinity. So it does make the things better for us, basically. So as of now, the two things we have discussed, the bag of word model and this distributed bag of words model, both of them are kind of there is a fundamental issue in both of them. The first thing is it requires a very large dimension vector to represent its meaning. Okay. And also it's very sparse. Because not all the words have been correlated with all the words. Okay. So maximum elements in a co-occurrence matrix will be 0. So the representation for the each particular word and its vector maximum elements will be 0. It will be very sparse. Okay. And as the size of our vocabulary increases, uh, this co-occurrence matrix will be over to the power, means it will increase exponentially, basically. Okay. So the question now, the next question we are going to be asking is that can we do better? Okay, instead of falling into these traps, okay, can we have a different solution for this? Okay. This solutions are kind of a very much brute force, and it does the work what we want. But as it has a fundamental issues as I discussed, it's very sparse, high dimension, and it increases with the vocabulary size and all. Okay. So computation, it's very heavy in simple words. Okay. So we'll be asking that can we get a more compact and a smaller representation for represent this word to a vector representation. So the solution we are going to be looking is the SVD, that a dimension reduction we are going to be doing. Okay. So SVD for learning the word representation. Okay. So what is an SVD basically? So basically the SVD, in SVD we have been given a suppose we have been given a certain matrix. Okay. And the matrix, it can have a very much high rank. Okay. But can we have a very low approximation rank for the matrix so that if we reduce the number rank for a matrix, we are not using much information basically. So can we represent a very large matrix using a 10 rank matrix? So that's the question we'll be asking. So we have been given a vector x, matrix x, which is of the size m cross n. The number of rows are m and the number of columns are n. Okay. So using SVD, we can decompose into we can do the SVD on the matrix, okay, and we want to get a rank K approximation for the given matrix, okay. So we want to decompose into U M cross K, where is K the rank approximation you want for the given matrix, okay. Singular value K cross K and B K cross N. So the dimension matches, you can check it out, okay. M cross K is there, K cross K cross N is there. So if you multiply all of them three, we'll be getting M cross N, the same shape, basically, okay. And so we want to do SVD on the co-occurrence matrix we have defined before, okay. The purpose is that we want to get a rank K approximation for the co-occurrence matrix so that it's very much easy for us, okay. Computation, it will be very much easy and efficient, basically, okay. And also the thing is that we want to means identify certain meaningful semantics in our representation. We want to give away kind of over information we are having. Okay. So that's what this rank K approximation will be doing us. It will be just giving us top K rank 1 matrix. Okay. Which is having a kind of a similar information as X. Okay. So we have been given X. We want to decompose X into a K rank matrix, means total, means rank 1 matrix of and total number of this matrix are K. Okay. So you can compactly represent it as summation over I from 1 to K, sigma I, Ui, Vi transpose. So this is a compact representation of this SVD thing. Okay. So where sigma I is the means Ui, Vi is just a vector. And this matrix Ui, Vi transpose, it will be a rank 1 matrix. And this sigma is kind of a weighting term, averaging. Okay. So singular value, we call it as basically, okay. And we want to find the top K such matrices, okay, for the X. So for example, if K is 1, then we are asking the question that we want to get a best rank 1 representation for the X, okay. If it's 2, then it will be a top 2, okay. So if you do the rank SVD decomposition, okay, you can order the singular values and you want to keep a singular value based on its magnitude. The larger the value is, then if you want to K, then the top K magnitudes of singular values you are going to keep for the approximation. Okay. So there have been a very nice example in this week lecture as well. Okay. So for example, we have been given a representation, 8-bit representation of world. Very right is there, very light green, dark green, very dark green. So very light, dark, very dark. We are representing using a 4-bit, and green we are representing as a 4-bit number. And suppose we want to get approximate this vector using just a 4 bits. So we want to give away the extra information, but we want to keep the more semantic meaning basically. Okay. For example, cat is there, cat is having a 2 there, something of this particular color and all. So each word is having a representation. But suppose if I want to say that represent cat with just a one vector. So you want to give away its information about its color and rest of the stuff. Okay. So that's how. So we are given the example, we are given 8 bits to represent a color. So we are given, we be just, if you want to approximate using the 4 bits, then the top 4 bits, which give us the dark, light, very light, and very dark, we are going to be give away. So it's kind of a approximation we are doing it. We want to give away the extra information, but try to keep the more useful information so that our representation does not become useless kind of stuff. Okay. So now the X is there. X represent the co-occurrence matrix. So we can define X cross X transpose as well. Okay. So the ith and the jth entry for this thing, it will be giving us the representation of the word I in the X at ith row and the word at the jth column, where jth row basically. Okay. And in this case, X transport, it will become a jth column basically. Okay. So we are just trying to calculate a similarity between, means dot product between the representation between the word I and the word J. Okay. So that is what this X transpose will be giving us. Okay. So it's kind of giving us the cosine similarity between the two different words, that how these two words are correlated, how much. Okay. So means we are moving in the direction where we wanted basically. Initially, we wanted to have a representation from word to vector. We defined it that using the one-hot representation, but there were certain traps there that it does not convey the proper meaning of the word. Every word was two times away from the other word representation. So we defined the cosine similarity that if we have a cat, dog, it should be very much nearby. If we have a truck and car, it should be very much far apart from the normal cat, dog representation. So that's how we will be using X into X transpose. It will be giving us the dot representation between the word I and the word J. Okay, how much these two are correlated. Okay. And doing such thing, it will be giving us more, it will represent, means give the kind of a latent representation and latent semantics for the underlying vocabulary, that how frequently each and different words are occurring all together. What's the correlation between these two words? Okay. So upon based on that, top of that, we can apply different tasks. Okay, classification, next word prediction, and all. Okay. So what if you simplify this X transpose? Okay, using the SVD decomposition. Okay. So we can write it as U sigma V transpose and U sigma V transpose transpose. Okay. It will boil down to V sigma U transpose. V and U are the unitary matrix. Okay. So it will be sum of two identity. Means V transpose into V will be identity matrix. We'll be getting it. So it will be sigma square U transpose. So this is how it will be boiled down. Okay. So it's equivalent to co-occurrence matrix times the co-occurrence matrix transpose. So conventionally, we can define this U sigma as U sigma transpose. Okay. So U sigma is kind of a, means context kind of. It's a word basically how we have defined, but V is there in the singular value decomposition. That's the context. Okay. So U sigma gives the representation for the word, and V give us the context on which we are projecting our U sigma. Okay. So that's was about this distributed representation for the blending the from words to vector form. So now we'll be talking about continuous bag of words model. So as of now, we have seen the counting based model, and using the, we were just counting. We would define the context here. We were defining that in that particular context and how many times these two words are occurring together. And based on that, we defined the co-occurrence matrix. Okay. And we did SVD on top of that. So now we will be defining a continuous bag of models. So by the name itself, we want now we will be moving towards more continuous vector representation for the words. Okay. So now we will just try to see the methods where we will be trying to run the word representation by directly running the next word prediction. So we be defining the context length as same as it is. So we be giving the previous word and try to predict the next word. And during this procedure, we will trying to run the co-occurrence matrix. Okay. So what's the task here basically? The task is that we have been given nth word. We need to predict the nth word given the previous n minus one words. That's the task. So we have been given n minus one words. We want to predict the next word basically in the vocabulary. What's the probability of having this next word prediction? Okay. So let's take a very simple example. He sat on a chair. Okay. He sat on a chair. Okay. So we will be passing he sat on a and asking the question, what's the probability that it should predict the chair? But okay. So we have been given a corpus different sentences. We be again defining the context and dividing into a context size of certain length. And we'll be taking an n minus one words and try to predict in particular nth window. We're trying to using the n minus one words. We're going to be predicting the nth word basically. Okay. So training data is already available to us basically, the corpus in the form of corpus. Okay. We'll be defining the using the corpus and word windows. Okay. We'll be just taking a context end of five, taking a initial first four words, try to predict the fifth word. Okay. So the question is that how we can model such representation or such model. Okay. So what's the connection between this task and learning word representation? So we are going to be using feed-forward neural network, which we have already seen the previous weeks. Okay. So first of all, we will be defining a one hot representation for the context word. Okay. So for example, if we have been given a word set, so what's the probability of he given set? What's the probability of chair given set? What's the probability of man given set? Okay. On the we be having vector size binary string basically of size not binary string. It's a we be having r to the power n, where n is the vocabulary size length vector, and the summation of all the representations should sum up to one. And we'll be asking that what's the probability of occurrence of this words given the previous one. That is the conditional probability we are asking here. So they are total in the vocabulary. Suppose the number of words are suppose I denoted by V. Okay. So there are now V words are there. So we want to do it's kind of a multi-class classification task. Okay. We be inputting conditional variable that is a set, and we'll be trying to predict the next word. So it needs to introduce, we need to introduce a probability that given a certain word, what's the probability distribution of predicting the next word. So as we have seen that this co-occurrence matrix, we define a W word and W context. Okay. Now we are being doing the task of learning the next word prediction, and using that we want to learn the representation for each and every word. Okay. So the the task is basically like that. We will give to our feed-forward neural network. We're giving one hot representation of the word, and it needs to predict the next word, conditioning on that particular vector. Okay. So this can be very much intuitively represented as this three layers neural network We have first here is our input, in between is context size, and the last is the probability distribution of predicting the next one. Okay, so the input is our input is just R to the dimension of V basically, because the number of vocabulary is V we are taking. Then the weight for this matrix will be calling as a context. Okay, which will be of the size of R K cross V. So we will be giving us a vector of size K, which is kind of a context. Okay, now using the context vector, we are gonna be, we want to predict the next word. Okay, so this W word vector is of the form RK cross mod of V. Okay, and it will be inducing a probability for that on the vocabulary size. That was the word prediction. And the task is basically we are being a corpus. We divided into a bunch of different for particular context. We have defined that what the next word is there, and it's similar to a multi-class classification problem. And we be certain loss as of now. I will be defining. So using the loss, we will be trying to run the representation and the context. What's the context representation for each and every particular word? So if we see this thing basically, okay. So this vector, the final vector we are getting y, it will be in the form of r to the power of v basically. Yeah. Okay. So what's the product of w context x? Given that x is a one hot vector, so it's just a ith column of the context. Okay. So whenever we have a matrix, okay, and we are multiplying it by the one hot vector, where only one index we are having one, rest of the indexes are zeros. So we are picking the ith column, which was non-zero in our vector whenever we do w context x. Okay. So in other words, there is a one-to-one correspondence between the representation w context and the words, because we are picking the ith or ith word, we are picking the ith column from our context matrix. Okay. But now the question is that how can we obtain probability of a particular word, suppose on given set? Okay. So this is, as I mentioned, this is a multi-class classification problem where we are having a number of classes is is the size of the vocabulary basically. Okay. So here our friend will be coming into a picture that is a softmax, because it will be giving a bunch of numbers. Okay. And all the numbers does not sum up to one. For the probability distribution, we need to make all of them positive, and the summation across all of this vector should sum up to one. So that's why we will be using a softmax here. Okay. So it will be giving us a logic, and on the top of logic, we will be defining a softmax. So the probability of a word on given set is proportional to the dot product of the jth column of the context and the ith column of the word. So it's kind of a similarity we are measuring it. That's given, for example, whenever we are conditioning, after conditioning, we are picking the jth column from the context, okay, and ith column from the word matrix. So we are just measuring the similarity between these two things. Okay. So now the question is that how can we run such model basically? Okay. So we will be defining the same loss we have defined in the classification in the previous weeks. That is the cross entropy loss. So the cross entropy loss is defined as minus log of y predicted. So it's equivalent to minus log probability of word given a context. Okay. So y is just softness. So we can just substitute in the loss and get a full expansion basically. So using now we know that how to learn this thing. We have a loss defined, we have a model defined, we know the meaning that what this model is learning basically. So for learning this model, we are going to be using just a back propagation. Okay. So we have been given input, we have defined the loss, we have defined the model. Okay. So we'll be using a back propagation and we'll be using our optimizer and just update our weights based on the gradient. So one thing, if you notice about this gradient, update you. Okay. So whenever we have our output is correct, okay, there won't be any update in the weights. Okay. But whenever our output is wrong, okay, there will be update in the weight. So it will be moving a fractional or a very small quantity towards that direction. Okay. So that's was a very nice interpretation for using a soft means cross entropy loss where you are doing a multi-class classification. Okay. So now the question is, as we were conditioning on the one word, so what will happen if we condition on two words? So the same procedure we follow as it is. Our input we now will be of a dimension of R2V because V was the representation for the one word. As we are conditioning on two words, it will be 2V. If you are conditioning on N previous N1, then it will be NV basically. Okay. And but the context length, the context matrix will be changing in this case. Okay. So it will be a just concatenated version of W context with respect to each and word. Okay. And again, we will be asking the question that what's the probability of particular word given this conditioning on previous two words. So the interpretation for this thing is basically if we have a vector, if we are passing one hot representation, we are having at multiple indices one and rest of the multiple indices zeros. Okay. So it will be picking us the columns which are non-negative or which is positive or one. Okay. And it will just do the summation across that two and give us the just a sum of the columns for the sum of the columns for the non-zero indices for the given conditionals of order. Okay, but the thing is just training the models using conditioning on the previous n words. Learning this procedure is very means if you want to condition on previous 10 words or 15 words like that. It's very much expensive procedure. Every time you need to means the number of parameters in a model will increase exponentially. It will be better, but again, maybe asking the same question that can we have a much more better representation or much more competition should not be heavy that much. That's the thing. Okay. So now coming to the next model, that is a skip gram model. Okay. So in the skip gram model, as we saw the continuous bag of model, we were using try to predict the next word. Okay. So it predicts the output give a bags of output in the continuous words bag model. We were using the previous n minus one words try to predict the nth word. Okay. So in the skip gram, there is a very slight change. Means we be the context and the word, the matrices, it will just getting changed. Okay, which predicts the context word given an input word. So instead of word given context, we'll be asking the context given word. Okay. So again, the procedure we follow same as the bag of word. And again, the problem is the same. It will be computationally expensive. Okay. And the softmax function at the output is okay. So the solution for this is just to we'll be using a three solution for it. That is a negative sampling, contestive estimation, and hierarchical softmax. So we'll be looking this three solution. And after that, we'll be just solving the assignment line problems. Okay. So the first thing is the negative sampling. Okay. As computing this softmax over the vocabulary size, it's kind of a very much computationally heavy. Okay. So what does in the negative sampling we do is that we're picking a word and a context. Okay. So we'll be defining the same corpus. Okay. We'll be having, for example, set on, set a, set chair, like that. Okay. So we will collect all such pairs of words and context. Okay. From a corpus. And we will be defining an incorrect set as D bar. So we'll be defining D and D bar. Okay. Which is an incorrect. That is set oxygen, set magic, something like that, which does not have any meaning at all. Okay. So that is an incorrect pairs of in the corpus. And the D dash we can construct by random sampling a context word R, which was never appeared with W and create a pair W cross R. So we can just look into that whenever these two words are not occurring together. Okay, that means that it's a negative pair basically. So again, we'll be interested in maximizing the probability, or we'll be just using a softmax. We'll be trying to predict a random variable Z. What's its probability of one given particular D? That is a word and context, which are positive samples. So we are interested in maximizing uh, vector representation between a word and a context. And same follows for the negative samples. We want to maximize the probability. The similarity is zero. Okay. And combining both of them together, we can means the problem we were having in applying the softmax to the whole vocabulary size, it becomes much more easier. Okay. Because the negative samples we are at each and every iteration, we are going to sample the k size negative negative samples. So this is what happens in basically this negative sampling. In contestive estimation, now we'll be seeing, for example, the positive sample is there. He's set on a chair. Okay. Then he set oxygen a chair, suppose. Okay. So that's a negative thing. So we'll be using passing through a model, the set positive samples and context and try to predict the similarity. We will be trying to predict the output. Okay. So what we want is that the output for this set and the on, it should be greater than the set and the oxygen. So we'll be using a neural network. We are going to be passing two words, the positive samples and two negative samples, and we want to make that, for example, if it is very much correlated, the set and on, the vector it will be giving us. And when set and oxygen we are passing, we are going to give another vector, and we want to minimize that vector, the norm of that basically. Okay. So basically, we want to maximize the distance between this positive vector and this negative vector we are having. Okay. And we want them to be at least differ by means m distance. Basically, that two vectors should be at least m distance far apart. Okay. So the same procedure we will be following. Okay, that if S is very much larger than SC plus M, then we won't be doing the backpropagation with our model. If it is not, we need to follow the backpropagation basically. Okay. Then we'll be discussing the next uh, solution, that is hierarchical softmax. So what happened is that basically in the output layer for this continuous bag model, the size for the vocabulary was large. and to compute a softmax on the top of that was computationally heavy. Okay, so we be taking a random we can just we can construct a binary tree basically. Okay, such that all the this vocabulary words are there, they will be a leaf node. Okay, so given a certain random sequence, okay, we be gonna constructing a binary tree on the top of that. Okay, and there exists a unique path from the root to a leaf node. It is true for the uh, any path between two nodes in a tree, because there we don't have any circle or multiple paths. They always exist as only one path only between from any two nodes. That's the property of the binary tree. Okay. So suppose traveling from the top to the particular word, okay, nodes, we'll be assigning a random vector, a random binary vector. Okay. If we are traversing towards a, if we are at a particular node, and in the next instance, if we're traveling towards a left side, then we'll be giving that random vector in that particular node as one. Otherwise, if it is on the right, it's zero. Okay. So finally, each internal node is associated with the vector ui. Okay. And so the parameter for the modules are w context u1, u2 till uv. Okay. So for the given pair of the word and the context, we are interested in the probability of w given a particular context. Okay. So we can model this probability by having a product of the random vector which we have defined from top to from the root to the particular leaf. Okay. So what we are saying is that the probability of predicting a word is the same as probability of predicting a correct path from a path from the root to that particular node. Okay. So that's it's equivalent. Okay. That we be starting from the root and predicting the next word, the probability, it almost boils down to the same as predicting a unique path. So there is a one-to-one corresponding between these two. Okay. And again, maybe with the high similarity between the particular and path, okay, we want to maximize the probability. Okay. So the main advantage for this thing is that it does not require a softmax. Okay. So here, the only thing is that we need to construct a binary tree, and even any random binary tree works out here in this case. Okay. So that was the sum of the representation technique which was covered in this week. Okay. So now we'll be moving towards solving some of the problems from the week 9 actually. Okay. So we have been given a one-hot representation for the two words, that is apple and a ball. Okay. So for the apple, it's 1 0 0 0 0. It's in the fifth dimension. And for the ball, it's 0 0 0 1 0. So it's just two binary string of the length of 5. So the Euclidean L2 norm between these two distances is very easy to calculate. Okay, just take a difference of each and every component, square it, and take a square root. The answer for this is just root 2. Okay. So it was the one-hot representation based on one-hot representation vector. Okay. And it's always root 2 in that thing. Now we have been given a corpus. Answer the question based on a given corpus. So for this question, it requires just to manually calculate the size of the vocabulary and all. Okay. So that's pretty much easy. Okay. We can just count the total number of different words. So that I'm not gonna do. Okay, that's as I'm leaving as an exercise for you. Okay. So we have been given a corpus of certain different words. Okay. So they have the first question they have asked is what's the size of the vocabulary? Okay. So we need to count the number of unique words. Okay. That's very simple exercise. And suppose we want to calculate a covariance matrix using a corpus M. What will be the value of the M given and A? So we have been given two words and a context length of two. Okay. So we need to count a number of, we need to divide our corpus into a length of two. Okay. And ask the question that how many times these two words have occurred altogether. That's also a very pretty straightforward task. Okay. Now we are to build a vocabulary using a corpus given above and use one hot encoding to represent a word. What's the ideal dimension of the word hot encoder vector? Okay. So the number of unique word is total 31. Okay. And we have been given as that we want to build a vocabulary using this corpus and one hot representation. Okay. So it's from the information theoretic point of view that if we have 31 numbers, means how much you can compress using zeros and ones. Okay. So there is a straightforward answer for that is that you need to take a log of that. So if I have a 32-bit information is there, okay, means 32 size, okay, then I can represent that using a log, the number of different vocabulary size in the we are having to the base of 2. So in this case, the number of total unique words we were having was 31. Okay, so it will be log to 31, and we can take a lower ceiling for top of that. So it will be 5, basically. Okay. Now coming to fifth question. After doing the SVD on the co-occurrence matrix, we find that the anti-I. So we have been given an co-occurrence matrix. Okay. We have done the SVD on top of that. And the MIJ, when that's in that matrix, ith row and the jth column. Okay. As the particular highest value in the particular in the value in the ith row, where M is the row rank representation of the co-occurrence matrix. Which of choose the correct statement? Word J occurs many times in K span window of the word I. That's true. That's how we have defined the co-occurrence matrix. In a particular row, the highest uh, number or highest value we are having. That we denote that that particular word has a stronger correlation with that particular word in that particular context length. Okay. Word I and J have a high cosine similarity. That's automatically true. Okay. And Mi comma J is equal to Mj comma I. That's not particularly true. It can or cannot be. Okay. I and J are not the stop words. Okay. Now coming back to question 6, we add incorrect pairs into our corpus to maximize the probability of the word that occurs in the same context and minimize the probability of that occurs in a different context. Okay. This technique is called negative sampling because in a negative sampling, we have a positive pair and a negative pair. Okay. So that is also straightforward from the lecture material. Suppose we are given a training skip-gram model using a hierarchical softmax. We observe that the representation of the word apple and a fruit are very highly similar. The representation of the word banana and the fruit are also highly similar. What, which of the following statements are true? Apple and fruits are contextually related. That's true. Okay, because the cosine similarity is higher. And the apple and banana will have a high similarity according to the representation done by a model. That's also true because that's a between two vectors, if vector A and B are very much highly correlated and B and C are highly correlated, then the vector A and C is also correlated. That's by the definition. Apple and banana will not have a highest similarity according to the representation. No, it is having. So A and B is correct. Apple and banana will have a low cosine similarity. No, that's also not true. Now coming back to question 8. Suppose we are learning a representation of a word using a globe representation. We observe the cosine similarity between the two representation Vi and Vj for I word for the words I and j is very high. Which of the following is true? Okay. So Bi is 0.02, Bj is 0.05. Since the word representation Vi transpose Bj is Xij minus Bi minus Bj. So Bi they have given us 0.02, Bj they have given us 0.05. Okay. And cosine similarity is very high. So this quantity is very high. Okay. So the hence the value of this will be, this is positive. High in the means positive. So the if we add this two, it's kind of a 0.07. So Xij, this quantity is negative and this quantity is positive. Okay. So if you take this to this side, this whole thing will be very much positive basically. Okay. Hence Xij will be high, but only high value, but the only high value for Xij is 0.8. Okay. So it can't be 0. It can't be 0.03. So it is very much very high. So the 0.8 is the right answer. Now coming back to question 9. Which of the following is true? SVD with tuned hyperparameter gives better result than predicted based model. With tuned hyperparameter give us better result than predict based methods on the analog task. Yeah, that's true. Because SVD we are doing in the representation in the next word prediction, it's equivalent to SVD. SVD and word to vec have a different underlying principle, hence give a diverse answer to the same question. That's false. Okay. Predict-based method like word to vector have more computational efficient than SVD. That's true. So correct option is A and C. Which of the following technique is used to evaluate the word representation by a model? Semantic relatedness, synonym detection, analog task, all of the above. So the answer for the test is all of the above. So that's all for today's lecture problem solving. So if you have any question, do put in the comment. So I hope you liked the today's session. So thanks for attending the today's session.